Okay, so now we see how it works. It's really going to be pretty, most of them will be straightforward. Some of them will be a little bit tricky. So if we look at this circuit on B, we see that we have the AND of Q1 and Q3. So we need Q1 and Q3 to both be 1s. And the first time that happens is going to be when it loads again. So we have Q3, Q2, Q1, Q0. It loads with 0, 0, 0, 0. And the first time we get Q3 equal to 1 and Q1 equal to 1, that's going to be when we reload. So we'll go ahead. Well, let me do this. Maybe I can learn to count. Okay, so if these are our numbers, and that's Q3, Q2, Q1, and Q0, if we start with 0, 0, 0, when is the first time we get to where Q3 and Q1 are both 1? Well, we know Q3 doesn't become 1 until we get to 8, so it's going to be after 8, and then the first time Q1 is 1 after that is when we're at 10. So the first time that we're going to get to a Q3 and a Q1 equal to 1 is at the number 1010. And in general, the smallest number that has 1s in certain places will have 0s in all the other places. Because anytime you have a 1 in a place, that would make it that number bigger than if you had a 0 in that place. And so if all I'm looking for is this AND of these 1s, the smallest number that'll have that will be the one that has 1s in that place. And so in this case, that would be 10. And so my count sequence would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0. Okay, all right, so let's go on and look at the questions on that. Okay, so this one is slightly different because of where we're loading. So we load with Q0 and Q2 equaling to 1. So that would be, so this is Q3, Q2, Q1, and Q0. So that number is 5. We still have that we're going to stop, we're going to reload when Q1 and Q3 are both 1s. 5 is definitely less than 10. And if I'm counting in order, if I'm starting at 5, the smallest number that'll have both 1 in Q3 and a 1 in Q1 is going to be 10. So this is going to go from 5 to 10. Once it gets to 10, it reloads, and what's it going to load to? It's going to load to 5. And then it'll count, the next number will be 6, and so forth. And so our count sequence will be 5, 6, 7, 8, 9, 10, and then back to 5, 6, 7. Does that make sense? Any questions on that? All right. Let's see, I don't have my chat open. Yeah, so I'll go 5, 6, 7, 8, 9, 10, 5, 6, 7, 8, 9, 10, 5, 6, 7, 8, 9, 10.
So it resets to 5 every time?
Yes, and the reason for that is because that's the number that's here on these load wires. And so every time it loads, it goes to that. And the counters, and like he said, we're using this specific type of counter. This specific type of counter doesn't have anything in place to say go to 0. The only thing it has is load, and you'd load whatever would be there. So it would make sense that a counter would be able to go to 0, and I think the one in the book does. I think that's what that reset in is for, but this one does not. And I know I had somewhere. There it is. Okay. All right. All right. So if there are no questions, I will go on and we'll look at D. So D, we're putting two 4-bit counters together to make an 8-bit counter. And if you didn't watch the first video that had the explanation of how the counters work, go back and watch that, and then this will make sense here. So this is going to count up all the way until we see that 0, 1, 2, and 3 are all ones. And then what happens is that enables the second counter. And so if you think about that, that means that the second counter, if I call this C1 and C2, the second counter is not enabled until the first counter gets to all ones. So the first counter has all ones. I mean, it starts with, assuming it starts with a load of 0. It doesn't show that, but let's say that it does. So it starts with zeros, and then there's nothing to tell it to change whether it should load or not. The load is being shared between the first counter and the second counter, and all we see on it is some value LD, which we don't know what that is. And then it's going to, so this is going to count until it gets to all ones. When it gets to all ones, it enables the second counter. So let's assume, I erased this on purpose. Okay, so this is, the right one is counter 1, the left one is counter 2. So counter 2 doesn't change until we get to all ones here. And when we get to all ones here, that enables the second counter, so it says, yay, I get to count. So the next thing it does is it counts the way it's supposed to. So this counter right here will go to 0, 0, 1. Nothing has told the first counter to stop counting. It's at its full 1, 1, 1, 1. The next thing it does is go to 0, 0, 0, 0. And now if you look, Q0, Q1, and Q2, Q3 on the first one are not all ones anymore. So poor counter 2 is not enabled anymore. So it just has to sit there. So it's going to stay 0, 0, 0, 1 while the first counter goes through its whole count sequence again. It's going to stay with 0, 0, 0, 1. Until the first counter gets back to 1, 1, 1, 1 again. When it gets back to 1, 1, 1, 1 again, if you think about what I said at the beginning of this, if this were an 8-bit counter, this bit right here, bit 5, would look to its right and say, hey, everybody to my right is 1s. That's my signal. That's time for me to toggle. And so what would happen is this would then count, and all these would turn to zeros. And now counter 2 is stuck again at 0, 0, 1, 0, and then this one will start counting. So it does, having this in place has the same effect as the way I said the counter worked in the first place, which is when everything to your right is a 1, then you toggle. And if everything to your right is not a 1, you stick where you are. So let's look at what these numbers are. This 1, 1, 1, 1, this was 15. This is 16. This is 17. If we now think of this as an 8-bit number, so Q7, Q6, Q5, Q4, Q3, Q2, Q1, Q0. This is 17, this is 18, 19, and then when we get here, we would have 15 plus 16 is 31, and then the next one is 32, and then 33, and so forth. So the way you put two counters together to make a larger bit counter is you just put the AND of all of the bits and link that to the enable. Okay, so this is, that was D. Okay, so this counter is going to go all the way from 0 up to where we get all 1s in both counters. And if we think about our place values here, this is 1, this is 2 to the 0, 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th. And so all 1s is the same as 2 to the 8th minus 1. And 2 to the 8th is, let's see, so 2 to the 4th is 16, so that's 16 times 16 minus 1. 256 minus 1, or 255. So the count sequence is 0, 1, 2, 3, up to 255, and then back to 0, 1, 2, 3.
Why are you doing a minus 1? Where's the minus 1
Why did I say that all the 1s was, okay, because, so if I'm looking at a binary number, and I look at my place value, this is the 2 to the 0, 2 to the 3rd, 2 to the 1st, 2 squared, 2 to the 3rd, and wherever I have a 1, it has that value, so this number is 1, 2, 4, and 8. So this number is 8 plus 4 plus 2 plus 1, which is 15. That number is 1 less than what I would get if I had a 1 in the next spot. And so if I have yeah, so if I have 4 bits, then that, if the 4th spot right here, that is 2 to the 4th, that is the 16th spot, but with 4 bits, I have 1 less than having the 1 here. Does that Did that answer that at all? Yeah. So that's why. That's where the -1 comes from. So if I wanted to say, if I wanted to do, say, 256, 256 is that 2 to the 8th? I think it is. So actually, this is might be important for you, like in Verilog, when you have to have a number, you have to know how many bits it needs to take up. So actually, this is a good look at that. So let's say I want to do 2 to the 2 to the 8th is 256. Okay, so let's say I had 2 to the 12th is 4096. So if I wanted to have the number 4096, then I would need to make sure 3, 4, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What number did I just do to the 12th?
Yeah.
Okay. 4096 would be a 1 followed by 12 zeros, or so 4096, and so, or it would take up 13 bits, because the biggest number that I can get with 12 bits is 2 to the 12th minus 1. So if you're ever trying to figure out, say I need to be able to make my clock, I need to have a number that goes up to 20 million. Then you need to find what power of 2 gives you a number that's bigger than 20 million. So 2 to the 25th is bigger than 20 million, 2 to the 24th is smaller than 20 million. So if I have bits, like in Verilog, that go from 24 to 0, that means that I have a total of 25 bits that I'm using, which would give me 2 to the 25th minus 1 would be the biggest number I could have. So that's just a little help for you there. All right, and then going on to our last one here. Okay, so now we've seen that by putting these, making the AND of the 3 right here, that and turns this into an 8-bit counter. So officially now we can say these are bits 0 through 3 and these are bits 4 through 7. And let's see what's going on here. We have a single value is going to the load. And what is going to the load? So the load for both of them is the AND of Q3 and Q4. So let's look at what that number would be. So 0, 1, 2, 3, 4, 5, 6, 7. And we had Q4 and Q3. Notice this, we're not starting counting at 0, we're starting counting at we're starting counting at 1 0 1 0 0 0 0 0, and that number is, this is the ones place, the twos place, the fours place. This number is 5. So we're starting counting at 5, and nothing is, it's going to keep counting until both Q3 and Q4 are 1. And that's not going to happen until we get to, so this is 1, 2, 4, this is 8, this is 16. So that means we have a 1 in the 16's place and a 1 in the 8's place. That'll happen when we get to 24. So when we get to 24, then that makes the load equal to 1 on both of these, and so then it's going to start counting again. So this counter is going to start at 5 and count up to 24 and then go back to 5. Okay, are there questions on that?